For millions of years they have ruled the oceans. They are nature's most perfect predators, the shark. We often see them as simple, brutal hunters, creatures of instinct, but this view misses the true story. The real secret to their long reign lies not just in their teeth, but in their design. A design governed by the hidden laws of physics. They are masters of a secret technology. A technology written into their very skin, their muscles, and their bones. A technology that allows them to move through water with impossible grace and deadly efficiency. Imagine a world far denser than our own. A world where every movement requires immense effort. This is the world of the shark. Water is over 800 times denser than air. Moving through it should be difficult. It should be slow and draining. Yet, the great white shark can accelerate to incredible speeds in an instant. The mako shark can leap high out of the water. The hammerhead can turn on a dime with baffling agility. How is this possible? This is the paradox of the shark. How can such a large animal be so fast, so agile, and so efficient in such a challenging environment? The answer is not simple. It is a story of incredible biological engineering. It involves fluid dynamics, biomechanics, and material science. We need to look closer. We need to look past the fearsome reputation. We must ask new questions. How does a shark's skin help it slip through the water? How does the flick of its tail generate so much power? How does it sense the faint electrical whispers of its prey hidden in the dark? These are not just biological questions, they are questions of physics. And they challenge everything we thought we knew about these ancient animals. To find the answers, we must become detectives. We will peel back the layers of this living machine. We will explore the forces that shape its every move. We will see how evolution has harnessed fundamental principles to create a supreme hunter. This journey will take us deep into the world of shark science. We will uncover the elegant solutions that nature has perfected over 450 million years. Prepare to see the shark not just as a predator, but as a marvel of physics, a master of a powerful, secret tech that has allowed it to dominate the seas since before the dinosaurs. To truly understand the shark's secret technology, we need more than just beautiful underwater footage. We need to go back in time. We need to dig into the hidden history of scientific discovery, in vaults and laboratories, forgotten films, dusty documents, groundbreaking data. This is our treasure trove. Archive-first approach. We bring history back into the light. Archives hold the key to the physics of the shark. Rare archival footage of early experiments, early toe tank tests. Scientists pull shark models through water to measure drag. Black and white montage. Scientist adjusting a model in a water tank. Close-up of a technical drawing. Old photograph of a dissected shark. Classified documents from decades ago about bio-inspired design. First scanning electron microscope images of shark skin. These are not just artifacts, they're building blocks of modern understanding. Step-by-step scientific inquiry. Challenges. Step-by-step scientific inquiry. Breakthroughs. Not just the past, we pair archives with cutting-edge science, mathematics, physics, simple equations that govern lift, simple equations that govern thrust, stunning visualizations of fluid dynamics around a swimming shark. Boundary layers, vortices, pressure waves. We make the complex simple and the invisible visible, revealing the physical principles that make a shark a shark. This documentary is a promise. A deep dive into biomechanics of the ocean's top predator. A visual spectacle blending grainy history and sharp modern clarity. Dermal denticle, a shark's tiny scale. The powerful lunge of a great white. By the end, you will understand the secret tech of sharks. You will see them not as monsters but as masters of physics. You will never look at them the same way again. To understand the shark, we must first understand its world. It is a world fundamentally different from our own. We live in air, a thin and forgiving medium. Sharks live in water, and water is a physical bully. Dense, viscous, relentless. Every single movement from the slightest twitch of a fin to a full-speed predatory dash is a battle against the immense resistance of this fluid environment. Imagine trying to run through a swimming pool. The water pushes back against you with incredible force. This is the shark's reality. Every moment of its life. This constant opposition is the defining challenge of underwater existence. Water is over 800 times denser than the air we breathe. It is also 50 times more viscous, meaning it resists flow more strongly. Think of it like walking through honey instead of air. This density and viscosity create a wall of water that an animal must push aside to move forward. For a large creature like a shark, this requires an enormous amount of energy. The physics of this fluid world dictates everything about the shark's design. It is the ultimate sculptor shaping the animal's form over hundreds of millions of years. So, how does the shark not only survive, but thrive in this challenging environment? It has evolved to become a master of fluid mechanics. It doesn't just fight the water, it manipulates it. It bends the laws of physics to its advantage. This mastery is not a conscious choice. It is written into every curve of its body, the texture of its skin, the rhythm of its tail. The shark's body is a living textbook of hydrodynamic principles. It is a perfect solution to the problem of moving through a dense, resistant world with maximum efficiency and minimal effort. To decode the shark's secret technology, we must first learn the language of water. We need to explore the fundamental forces at play. We will investigate concepts like drag, lift, thrust. We will see how these invisible forces govern every interaction between the shark and its fluid home. By understanding the physics of water, we begin to see the shark in a new light. Not as a simple fish, but as a highly sophisticated biological machine perfectly tuned to conquer the unseen obstacle of its liquid universe. This is where the story of its physical genius truly begins. In the world of fluid mechanics, not all movements are created equal. The way water behaves around an object depends on two key things: size, speed. A tiny plankton drifting in the current experiences water very differently from a great white shark charging at its prey. To understand this difference, scientists use a special number. It is called the Reynolds number. It is a simple but powerful concept. It helps us compare flows across different scales and speeds. It tells us whether the flow is smooth and orderly or chaotic and turbulent. The Reynolds number is a ratio. It compares inertial forces to viscous forces. Inertial forces keep things moving. They relate to mass and velocity. Viscous forces are the sticky, frictional forces that resist motion. When something is very small and slow, like a bacterium, viscous forces dominate. The Reynolds number is low. The water feels thick and syrupy. Stopping propulsion brings an almost instantaneous halt, like swimming in molasses. A shark, however, is large and extremely fast. For a shark, inertial forces dominate. Its Reynolds number is very high, often in the millions. Once the shark gets moving, momentum keeps it moving. The stickiness of water is less the problem than the turbulence it creates. At high Reynolds numbers, laminar flow breaks down. It becomes a churning, swirling mess of eddies and vortices. Turbulent flow. This turbulence is a major source of energy loss. It's the hydrodynamic equivalent of a noisy, inefficient engine. This single number, the Reynolds number, is crucial. It defines the regime in which the shark operates. The shark's body is not built to swim in molasses. It's built to manage the chaos of high-speed, turbulent flow. This is the shark's engineering challenge. How can it move fast without wasting energy in a chaotic wake? The solutions: streamlined shape, the unique properties of its skin, precise fin control. The Reynolds number sets the stage and defines the problem that the shark's evolution has so brilliantly solved. Every object moving through a fluid experiences a force that opposes its motion. This force is called drag. It is the primary enemy of any swimming animal. For a shark, minimizing drag is a matter of life and death. Less drag means less energy is needed to swim. Hunting, growing, reproducing. It is the key to efficiency and survival. The shark's entire body is a testament to the evolutionary war against drag. It is a masterclass in hydrodynamic streamlining, honed over millennia to slip through the water with the least possible resistance. Drag comes in two main forms. The first is friction drag. This is caused by the friction between the shark's skin and the water molecules flowing past it. It is like the resistance you feel when you rub your hand over a rough surface. The larger the surface area of the shark, and the rougher its skin, the greater the friction drag. The second form is pressure drag. This is caused by differences in water pressure between the front and the back of the shark. As the shark pushes through the water, a high-pressure zone forms at its nose, while a low-pressure zone forms behind its tail, creating a turbulent wake that pulls it backward. We can even write a simple equation for drag: the density of the water, the cross-sectional area of the shark, and, most importantly, the square of its velocity. This last part is critical. It means that if a shark doubles its speed, the drag force it experiences doesn't just double, it quadruples. This exponential increase in resistance is a huge problem for any animal that needs to swim fast. It shows why even small improvements in drag reduction can lead to massive energy savings, especially during high-speed pursuits. The war against drag is a war of inches and percentages. The classic teardrop shape, known as a fusiform body, is nature's primary weapon against pressure drag. This shape, wide at the front and tapering gently toward the tail, allows the water to flow smoothly over the body and come back together with minimal disturbance. Archival, blocky model being pulled through a tow tank. Archival, streamlined shark-shaped model being pulled through a tow tank. It helps to reduce the size of the low-pressure wake, thereby reducing the backward pull. We can see this principle in the design of submarines, torpedoes, aircraft, but the shark perfected it long before humans ever dreamed of such machines. It is the first and most obvious piece of the shark's secret technology. Overcoming the constant force of drag requires an equal and opposite force. This forward-pushing force is called thrust. While the shark's body is shaped to minimize resistance, its tail is a powerful engine designed to generate thrust. The generation of thrust is an elegant dance of physics. The shark doesn't simply paddle the water backward, instead its tail acts like a flexible wing, or hydrofoil, using principles of lift to propel the animal forward. It is a far more subtle and efficient mechanism than brute force, turning a side-to-side motion into powerful forward momentum. The engine for this system is the shark's powerful swimming muscles, which run along the length of its body. These muscles contract in waves, sending a curve down the animal's spine. This wave of flexion grows stronger as it travels toward the tail. The result is that the tail fin, or caudal fin, doesn't just wag from side to side. It sweeps through the water in a complex, three-dimensional pattern. As the tail sweeps one way, it angles slightly, pushing water down and back. According to Newton's third law, for every action, there is an equal and opposite reaction. The water pushes the tail up and forward. This process generates two forces, lift and drag. But here the lift is not an upward force like on an airplane wing. It is a force directed sideways and forwards. As the tail sweeps back and forth, the forward component of this lift force is what propels the shark. The side-to-side components cancel each other out over one full tail beat cycle. The genius of this system is its efficiency. The shark's tail is designed to maximize this forward lift, while minimizing the drag it creates. The classic crescent shape of a fast shark's tail is perfectly optimized for this exact purpose. We can express this with a simple idea. The thrust generated is related to the mass of the water, move the speed at which it's moved, and the frequency of the tail beat. The equation for thrust shows that a shark can increase its propulsion by either moving more water with each beat, or by beating its tail faster. Different sharks use different strategies. A powerful lunge feeder might use a single massive tail stroke, while a marathon swimmer might use rapid shallow beats. It is a versatile system, allowing the shark to be both a sprinter and a long-distance cruiser, all by controlling this remarkable biological engine. Not all sharks are built the same, because not all sharks live the same life. The ocean is home to over 500 different shark species, each adapted to a specific niche. Their body shapes and swimming styles are a direct reflection of their lifestyle, particularly their need for speed. We can see a clear split between two main groups: the fast, open ocean hunters, the slower, bottom-dwelling cruisers. Form following function. The laws of fluid dynamics dictate available designs. Consider the shortfin mako shark. It is the sprinter of the shark world, capable of bursts of speed exceeding 70 kilometers per hour. Its body is the epitome of high-performance hydrodynamic design. It has a perfectly conical snout, a rigid muscular body that barely flexes, and a crescent-shaped tail with a high aspect ratio, tall and narrow. This design minimizes drag and maximizes thrust for explosive acceleration. The stiff body ensures almost all the muscle power transfers directly to the tail. The tail beats at a high frequency, generating incredible propulsion much like a high-performance propeller. Now, compare the mako to a nurse shark. The nurse shark is a slow-moving bottom dweller. It spends much of its time resting on the seafloor, or cruising slowly through complex reef environments. Its body is less streamlined, it is more flexible and flattened. Its tail is long and ribbon-like, with a much larger upper lobe than the lower. This design is not built for speed, it is built for maneuverability and endurance at low speeds. The long, flexible tail produces thrust with slow, wide, sweeping motions that lets the nurse shark navigate tight spaces and accelerate from a standstill without needing a long runway. These two sharks represent two different solutions to the problem of moving through water. The mako is a specialist in the world of high Reynolds numbers, where managing turbulence and minimizing pressure drag is paramount. Its body is a weapon for open water warfare. The nurse shark, on the other hand, is a master of low-speed maneuverability. Its flexible body and tail are perfect for the intricate, cluttered world of the reef. Each design is a physical compromise. The mako sacrifices low-speed agility for outright speed, while the nurse shark sacrifices speed for control, demonstrating the powerful influence of physics in shaping life. A cloak of invisibility. As a shark glides through the ocean, a very thin layer of water clings to its skin. This is not just any water, it is a special zone where the physics gets interesting. This zone is called the boundary layer. It is the interface between the moving body and the still, surrounding ocean. Right at the skin's surface, the water is stationary, held in place by friction. As you move away from the skin, the water speed increases until it matches the speed of the water flowing freely past the shark. The behavior of this thin layer is one of the most critical factors in the battle against drag. Ideally, a shark would want this boundary layer to be smooth and orderly. This is known as a laminar boundary layer. In a laminar flow, water particles move in parallel sheets, creating very little friction drag. It is the most efficient state. However, as the water flows along the shark's body, this smooth layer naturally thickens and becomes unstable. At a certain point, it will trip into a state of chaos. This is a turbulent boundary layer. It is a swirling, messy mixture of eddies that dramatically increases friction drag, stealing the shark's precious energy and slowing it down. The great challenge for the shark is to control this transition. It needs to keep the boundary layer laminar for as long as possible. But here lies a paradox of fluid dynamics. While a turbulent boundary layer creates more friction drag, it is also more energetic and sticks to the body's surface more effectively than a laminar one. A laminar flow separates from the body easily, creating a large, low-pressure wake that results in massive pressure drag. This phenomenon, called flow separation, is the main cause of drag on non-streamlined objects, so the shark faces a difficult trade-off. The ultimate strategy, then, is not simply to maintain a laminar flow. It is to control the boundary layer with precision. The shark needs to delay the transition to turbulence for as long as possible, but also ensure that when the flow does become turbulent, it remains attached to the body, to prevent a large drag-inducing wake from forming. This is a delicate balancing act. It is like walking a tightrope between two different types of drag. How the shark achieves this remarkable feat of flow control is one of its greatest secrets, a secret hidden in the microscopic structure of its skin. This is where our investigation must turn next. We have seen how the shark's streamlined body is its first line of defense against the tyranny of drag, but the war on resistance is fought on a much smaller scale. We must now zoom in, past the sleek silhouette, past the powerful muscles, onto the surface of the animal itself, like the shark's skin. To the naked eye, it looks smooth, like polished leather, but stroke from head to tail, it feels silky. Stroke from tail to head, it is rough, like sandpaper. This simple observation is our first clue. The shark's skin is not what it seems. This surface is no mere covering. It is a highly engineered dynamic interface between shark and water, a piece of natural technology, arguably the shark's greatest secret weapon. For decades, scientists suspected a role for skin in swimming ability, but lacked the tools to see it clearly. They could measure speed, they could measure water resistance, yet the connection remained a mystery. The skin held its secrets close. Hidden in a world too small for the human eye. To unlock them, we turn to the archives, pioneering mid-20th century studies. Scientists placed shark skin under early microscopes, intrigued by that sandpaper texture. What they saw was astonishing. The skin was not flat. It was covered in millions of tiny tooth-like structures, arranged in a precise, overlapping pattern, all pointing toward the tail, not scales as we know them. Something far more complex, a discovery that launched a new field. These structures are called dermal denticles, literally skin teeth. Structurally similar to teeth, they have a pulp cavity, dentine, and a hard enamel-like coating. The shark is covered from nose to tail in a flexible suit of armor made of teeth. This discovery posed a profound question. Why evolve such a complex, seemingly counterintuitive surface? Surely a smooth surface would be best for slipping through water. The answer would overturn decades of engineering wisdom and reveal a deep, subtle truth about fluid dynamics. Section 2. The dermal denticle, a microscopic masterpiece. The dermal denticle is where the shark's secret technology truly comes into focus. It is a marvel of microscopic engineering. Thanks to the scanning electron microscope, we can see these structures in all their intricate glory. Archival SEM images from the 1970s and 80s reveal a world of stunning complexity. Each denticle is not just a simple spike, It is a sculpted object, a flat grooved crown atop a narrow stalk. This design is no accident. Every feature, size, shape, spacing, is finely tuned by evolution. Different shark species have differently shaped denticles, each adapted to specific lifestyles and hydrodynamic challenges. Mako denticles, tiny, blade-like, with sharp, narrow ridges. They pack together into an almost continuous grooved surface. Lemon shark denticles, broader and more widely spaced. This variation shows denticles are not just for protection. They perform a mechanical function controlling water flow over the skin. The key feature, microscopic grooves or riblets, running along each denticle. The grooves align with the direction of flow. Their size, often only a few hundredths of a millimeter wide. That is a critical dimension. It matches the scale of the smallest turbulent eddies in the boundary layer. A tantalizing clue. Denticles weren't passive in the flow, they interacted with it at a fundamental level. A revolutionary idea. Shark skin as an active flow control device. Intricate shapes and patterns suggested a way to manipulate the boundary layer, that thin, critical region of water. The question how? How could tiny teeth and microscopic grooves influence flow around a creature thousands of times larger? Answering that requires a deep dive into turbulent physics, a realm where intuition fails. Throughout this film, we have celebrated the shark as a marvel of natural engineering, a master of physics. We have moved past the fear and looked at the function, replacing the monster with the machine. But in doing so, we must not forget that this is a living, breathing animal. It is a vital part of our planet's largest and most important ecosystem. The same adaptations that make sharks such perfect predators also make them incredibly vulnerable. Slow growth, late maturity. Few offspring. Today, these incredible animals are facing their greatest challenge, not from a natural predator, but from us. Overfishing, habitat destruction, the changing climate. It is estimated that 100 million sharks are killed by humans every year. We are removing these apex predators from the ocean at a rate that is simply unsustainable. The loss of these key animals has a cascading effect, unraveling the delicate fabric of marine ecosystems in ways we're only beginning to comprehend. The perfect machine is being broken. Understanding the shark, as we have tried to do in this journey, is the first step towards protecting it. When we see the shark not as a threat, but as a source of wonder and inspiration, our perspective changes. We see an animal of immense beauty and complexity, an animal that holds the key to incredible scientific insights and technological advancements. Its survival is not just important for the health of the oceans, it is important for our own sense of curiosity and our capacity for discovery. To lose them would be to lose 450 million years of evolutionary genius. So, the story of the shark is now in our hands. By supporting conservation efforts, making sustainable seafood choices, and fighting for healthier oceans, we can help write a better next chapter for these ancient mariners. We hope this deep dive into their secret technology has given you a new appreciation for these magnificent creatures. If you found this journey into the physics of the shark as fascinating as we did, please give this video a like. And to join us for more explorations into the science of the natural world, be sure to subscribe to our channel. Thank you for watching.